Welcome back, where we're going to continue our next discussion in Chapter 8 now. We pick up and we're going to introduce some new techniques of integration. So if you remember back in Chapter 7, we discussed all of our applications of integration. We looked at applications to geometry, specifically area, volume, arc length, and surface area. And we looked at one physics example when it came to work. And while all of those techniques all of those applications of integration were great, we were somewhat limited to the types of problems that we could solve because of our limited knowledge of integration. At this point, all we know how to integrate is either using our power rule, integrating it directly, or using a substitution, a U substitution technique. And what Chapter 8 will address now is all of the other techniques of integration that will help us tackle more complicated integrals. The first of those techniques that we are going to discuss today is 8.2, which is integration by parts. 8.1, if you want to, I encourage you to look in the text at section 8.1. 8.1 will go over all the techniques that we have available to us. It will remind you about U substitution. It will remind you about some algebra skills, splitting up fractions over numerators, multiplying by conjugates, things you talk about in Calculus 1. And so I encourage you, if integration isn't necessarily your strong suit and it's been a while, look at 8.1, review some of the things you already know how to do when it comes to integration, and then we pick up in 8.2 with integration by parts, our first technique. And so we'll pick up here, and to start off, we're going to remind ourselves of a Calculus 1 rule for derivatives. And when we learned how to take derivatives of products in Calculus 1, we learned that it was not as simple as just the product of their derivatives. We saw that the product rule, the way you take derivatives of products, because it has to give me the slope of the tangent line and has to actually mean something quantitatively, then the derivative would need to be the sum of two terms, where we have a product of f and g, and we take the derivative of only one at a time, i.e. it's kind of like derivative by parts. We only take the derivative of f times g plus f times the derivative of g. So derivative one at a time. And so in the same way, what we want to do today is we want to try to develop a rule for antiderivatives of products, or integrals when it comes to products. Now, we deal with products quite a bit when it comes to integration. We've seen integrals where there's products involved, but the products that we've dealt with have been related by derivatives, i.e. the chain rule. We've had a function and then the derivative is multiplied in. So it's not just a random product. Where here we're trying to address the idea that, well, what if the product of these functions are unrelated? What if they're not related by derivatives and U substitution doesn't work? How could we still address integrals when it comes to products? And so one way we can do that is by talking about a kind of integral version of the product rule. Just to simplify some notation, to get rid of the x variable, I mean, it could be t or z. Let's just talk about general functions. We'll call them u and v. And we'll talk about the derivative of a product u times v, where u and v are just some sort of function. Then the product rule says, well, in differential notation, du times v, so the derivative of the u term times the v function, plus u times the derivative of the v function, right? So it's the same exact rule, it's just a different notation. It'll just kind of make it a little more concise when we write down the integral version of this. And so what I'm going to do now to get an integral version is I'm going to take my product rule, and I'm going to integrate both sides of this equation. So I'm going to generate something like this. Integrals break up over sum, so I can do that. Integrate everything. On this side, we're taking the derivative of an antiderivative. And so they cancel, right? I didn't bother writing the differential here because we're taking the antiderivative of a derivative. So we get uv equals, well, we have, I'll write the differential second, v du, because that's how you standardly write integrals, plus u dv. And then all I'm going to do now is I'm going to move one of these terms to the other side. And so I'm going to choose to move the v du term to the other side. And therefore get an expression that looks something like this. U dv is equal to u times v minus this integral here. I'm going to subtract that integral to the other side. V du. U dv, uv minus v du. And we see why instead of using f of x and g of x, is using u and v kind of simplifies this notation. And this is going to be my integral version of the product rule. We call this integration by parts because the way that this process works is you get part of your solution every time you perform it. So the idea of integration by parts is we have an initial integral that we're starting with. Some initial integral that we're given, some integral that we need to solve. And say we don't know how to evaluate it. I can take this integral and rewrite it in this way. In this way, I get part of my answer, right? Notice that uv is not inside of an integral. It's just part of the answer to this definite integral, or this indefinite integral. Then we also get a new definite integral or a new indefinite integral to solve. But notice that they are not the same. They have switched in some way. And the relationship we have is quite an interesting relationship. You notice that while we have u here, in this new integral we have du, or its derivative. So we have a u and it's du now, its derivative. We also have dv here and v in this new expression. So it's the antiderivative of v in this new expression. So we've taken the derivative of u, the antiderivative of v, and created a new integral. In the hopes, the idea of it using integration by parts is maybe I don't know how to answer this integral, but if I take the derivative of one of these terms in my product and the antiderivative of the other term in my product, maybe that new indefinite integral I can solve. I still need to solve an integral. It doesn't give me the answer completely. It only gives me part of the answer and a new integral to evaluate. And the hopes is we can evaluate that new integral. I'll give you a very nice example for us to start. Say we needed to evaluate the indefinite integral of x e to the x dx. X times e to the x. And so we have a product here of two functions, x and e to the x. And u substitution doesn't work for me because this product is not related by derivatives. It's not like x is the derivative of e to the x. No, e to the x is not the derivative of x, so it doesn't really help me. I have no composition here in the exponent. And so I'm not able to use a u substitution. We don't have some sort of composition and a derivative multiplied in. But we do have a product. They're not related to each other. But what we can do is we can use this formula. I can take one of these terms in the product and let it be a u value. Take the other one, let it be dv, and then switch. Take the derivative of the u1, take the antiderivative of dv, and create a new integral for me, and also get part of my answer in the process. So the initial step of integration by parts requires you to at first choose a u and a dv. That is the first choice then that you have to make. You have to choose a certain term in this product to be u and another term in this product to be your dv. The idea is you want to make your new integral easier. So remember, whatever you choose for u, its derivative will be in this new integral you're going to create. Whatever you choose for dv, its antiderivative will be in the new integral you create. So we're going to use a little logic for a second, and we're going to look at these two functions. Let's look at e to the x. We know from calculus 1 that the derivative of e to the x is e to the x. And also that the antiderivative of e to the x is e to the x then. So it doesn't really matter which one we choose for e to the x. We're going to get e to the x in my new integral, right? The derivative of e to the x is e to the x. The antiderivative of e to the x is e to the x. And so regardless, this new integral will contain e to the x. So that one is irrelevant. Now let's look at x. The derivative of x is 1, constant. The antiderivative of x is x squared over 2. So now comes the question, would you rather have 1 times e to the x in your new integral, or x squared over 2 times e to the x? If you think about it for a second, you'd way rather have a constant. And so if I use some logic for a second, I would choose u to be x and dv to be e to the x. In doing so now, we will transform to a new expression. I'm going to use integration by parts to transform this indefinite integral to a new expression. I will get a new indefinite integral from it by taking the derivative of u, giving me x dx. Sorry, I need to put a dx here. All right, it's a differential, so dv is e to the x dx. And the antiderivative of e to the x is e to the x. So my new integral will contain this product. Oh, sorry, 1 dx. My new integral will contain this product. Along the way, the nice thing about integration by parts is you also get part of your solution. That's the reason why it's called integration by parts. You get one part at a time. And so you get u and v, whatever u and v is. So in this case, x and e to the x is part of my answer. So x times e to the x, uv, that's part of my answer, minus a new integral. So we still have to evaluate an indefinite integral, but hopefully it's easier than the one I started with. It's something that I can't evaluate. Remember, it's now this product. Well, that's 1 times e to the x, or just e to the x dx. Well, at this point, we can actually evaluate this directly. X e to the x minus antiderivative of e to the x, it's e to the x, and we're done, plus c, because it's indefinite. And we have our antiderivative. So up until this point, we have no way of answering this. Now we can. Let's try it again. Let's try x to the 5th times ln of x dx. Again, we have a product of two functions. They're not related by derivative, so u substitution is not a value to me at this point. And maybe I can transform the way this looks. I choose one of these functions to take the derivative of, the other one to take the antiderivative of, create a new integral that hopefully is simpler to solve, and maybe I get part of my answer along the way as well. And so we need to make a choice of u and a choice of dv. So we need to think first before we just jump the gun and make a choice. ln of x. Let's think about ln of x for a second. In Calc 1, we know that the derivative of ln of x is 1 over x. Antiderivative of ln of x, we actually do not know. In fact, what we're going to see in another video is to calculate the antiderivative of ln of x, you will actually need integration by parts. So just by the setup of this problem, it forces my hand in that I have to choose u to be ln of x. And therefore, dv is x to the 5th dx. Why? Is because I can take the derivative of ln, but I cannot take its antiderivative. I do not know it. And so we take du, which is 1 over x dx. That's the derivative of ln. The antiderivative of x to the 5th, I mean, we can still do it. It's power rule, right? 1/6 x to the 6th. And creating a new integral for me. So this product of these two things will be my new integral that I need to evaluate. And not only that, we also get part of our answer for free without doing any work. Part of my answer is u times v. So in this case, 1/6 x to the 6th times ln of x, u times v, minus a new integral. My new integral is this product. Now, although this seems complicated, remember it's 1 over x times 1/6 x to the 6th. So actually this x cancels with one of these x's, and I actually just end up with 1/6 x to the 5th dx. If I get x to the 6th over x, I can reduce the powers to x to the 5th. And now again, just like this one, we can evaluate this integral directly. And now we have our complete answer. X to the 6th ln of x minus antiderivative of x to the 5th is x to the 6 over 6. 1/6 out front gives me 1 over 36 x to the 6 plus c. Plus c because it's an indefinite integral, but we're able to evaluate it. And so again, we can evaluate more complicated products by using this technique. Again, the idea is we have a product, we take the derivative of one of those terms, we take the antiderivative of the other one, creating a new integral for me to solve, hopefully in a sense easier, something I can do. And in doing so, we also get part of our answer for free, right? Integration by parts. Part of the solution is given to you. And so let's go over and let's look at another example. So we're going to change up a little bit, we'll make it a little more complicated. Let's look at x squared sine of 2x dx. And so again, we have two functions multiplied together. They're not related by derivatives. We have a composition, I agree, but the derivative of 2x is 2, constant, not x squared. So it doesn't really help me. And so there's no way to solve this using a substitution technique. However, let's try to go integration by parts. So again, the first thing you need to choose is a u and a dv. Now I have to think logically for a second. This is the critical thinking part. Is if we think about sine for a second, who cares about the 2x? We'll address that in a minute. If you think about the function sine, regardless of whether you take the derivative or the antiderivative, you're either going to get cosine or negative cosine. So your new integral will always then contain a cosine in it. So regardless, it's cosine. Now what would be easier with cosine? Would I rather up the power of x by making it x cubed over 3, or decrease the power of x by making it 2x? Well, increasing isn't going to help me. Decreasing might. And so let's go ahead and make the choice then for u to be x squared. And then dv will be sine of 2x dx. So now we switch. We take the derivative of u, giving me 2x dx. We take the antiderivative of sine of 2x. Now, antiderivative of sine is negative cosine of 2x, and then the chain rule would require me to divide by 2. That is an exercise in u substitution. So I'm kind of shortcutting that. It's a very simple rule, right? Antiderivative of sine of mx will be negative cosine of mx over m, and that's just a quick exercise in substitution. But that would be the antiderivative. And therefore I get a new integral, and also part of my answer for free. And so part of my answer I get is u times v. So in this case we get negative 1/2 x squared cosine of 2x for free, minus a new integral. And my new integral is the product in blue. Well, in this case the 2's cancel, which is nice, giving me negative x cosine of 2x. Now I'll pull the negative out to make plus. And now we're at this point where here we now need to evaluate this definite integral. Unfortunately though, to evaluate this definite integral, we again need integration by parts. Why? Because, well, we still have a product. Product's not gone. And I still can't use u substitution. So we need to do integration by parts again. And so we iterate this process. I'll choose u and dv again for this integral. I'll make the same choice because, well, making a lower power of x is more useful. Create a new integral for me by taking the derivative of x, which is 1 dx. So at least now we have a constant in my new integral, so it's gone. And the antiderivative of cosine of 2x will be 1/2 sine of 2x. Antiderivative of cosine is sine of 2x, and then over 2 from the chain. So now if we continue on this process, we've iterated it twice. We have our first part of our solution we got for free when we did integration by parts the first time. We also get another part of our solution for free when we did integration by parts the second time. So that's my new u and v here, which is going to be x times 1/2. So plus 1/2 x sine of 2x. And then minus this new integral, which is going to be this new product in blue, which we have 1/2 sine of 2x times 1 dx. Now we still have one more antiderivative to take, right? We still have not evaluated the indefinite integral, but now we're at a point where we can actually evaluate this directly. And so now, after iterating this process 2 times, we are finally able to get to a solution. plus 1/2 x sine of 2x minus 1/2, well, antiderivative sine of 2x will be negative cosine of 2x over 2. We have it here. So we get negative, negative makes positive, 1/4 cosine of 2x. You get cosine of 2x over 2, so that makes the 4 in the bottom. The minus minus makes plus, and then plus c. Giving me my answer. Now, unfortunately, right, we see that we can iterate this process over and over again, and it might not be a very fun thing to do, right? For example, if we get the idea here now, if I write x cubed e to the 2x, we would have to use integration by parts 3 times in order to finally get to a place where we could evaluate the definite integral. I'll choose u to be x cubed every time, then decrease it to 3x squared, then to 6x, then to 6, and finally get to a place where we can evaluate the definite integral, or the indefinite integral. And so I hope that maybe there's a pattern that we can see and maybe get a shortcut. And so what we're going to do in the next video is we'll actually do this example, but I'm going to show you a shortcut way to do it. It doesn't apply to all scenarios, but it does apply to certain scenarios. So the scenario it applies to is when you can take the derivative of a term that eventually goes to 0, so pretty much polynomials. So if your u value, your thing you're choosing for the derivative, can eventually go to 0, which means a polynomial, then we're going to be able to use a shortcut. So in the next video, we'll get a shortcut way to evaluate certain types of integration by parts, which will make this a little bit faster. And then we'll use integration by parts to also answer some other types of integrals and also apply it to definite integrals. So part 1, we'll start here, stop here, and part 2 we'll pick up and do some more examples of integration by parts and take it and apply it to some other integrals as well. Other than that, I'll talk to you guys soon.